Charles Almeida from UFMG, and he will talk about Cayley-Hamilton algebras and beyond, an introduction to the geometries.
So, thank you, Hugo. First, I would like to thank the organizers for the opportunity to talk about this work that maybe seem a little misplaced in Algebraic Geometry and Commutative Algebra conference, but hopefully by the end of the talk I can convince you that we'll have nice interpretations for some algebraic facts here that, from the non-commutative world, right? So, to start, a general philosophy regarding commutative algebra, why commutative algebra is nice, at least for me, is that you can have nice geometrical interpretations from the objects appearing there, and you can use these geometrical interpretations to answer questions about the algebra, like can I have new potent elements? This algebra is a domain? And so there are examples of questions that we can make sense geometrically. And a very naive question is, maybe we can do this to non-commutative algebras too? What sort of non-commutative algebras can we make the same questions? So, of course, there is a very large field on non-commutative geometry, but maybe we can work our way on other kind of algebras and consider other kind of algebras here too. So, maybe the first encounter that everyone has with non-commutative algebra is the ring of polynomials, the ring of matrices and bi-n matrices. And to make things a little more touchable, let's think about the upper triangular matrices. And it's not hard to see that if we start with 4 matrices, upper triangular matrices 2 by 2, the commutator of these 4 elements is 0 for any 4 elements that I take here. So this means that if I consider this non-commutative polynomial here, x1, x2 minus x2, x1, I know this is maybe sound weird for us, but we can consider non-commutative polynomial variables here. By the fact that this vanishes, this means that by any 4 elements here in the ring of upper triangular matrices, this polynomial will vanish too. So this gives an example of algebra that we can make vanishes, that we can find a polynomial, a non-commutative polynomial, that it vanishes for all elements in there. So these algebras receives a nice name, which is called a PI algebra, or a polynomial identity algebra. So to make things more precise, if I start with a polynomial, with a non-commutative polynomial, I will say that this non-commutative polynomial is a polynomial identity for an algebra if this polynomial can be annihilated by all the elements of my algebra. Similar to what happens with the upper triangular matrices. So, if we happen to find a polynomial that can kill all the elements of my algebra, I call this a PI algebra, a polynomial identity algebra. So clearly, all commutative algebras are polynomial identity algebras because because all the elements satisfies this xy minus yx is equals to 0 because my algebra commutes. So every commutative algebras are PI algebras. So another nice examples of PI algebras are the upper triangular matrices, which is very easy to prove that they are PI algebras. But we can consider also the matrix algebra, and we can prove that the octonial algebra is also PI algebras. So besides that, we can also consider the ring of matrices, the algebra of the matrices. And we also, for each element inside there, for each matrices that we consider there, we can find a polynomial such that this element is the 0 of that polynomial, and this is the very famous Cayley-Hamilton theorem that everyone studies in linear algebra. So one thing that we should note that is the characteristic polynomial for that element can be expressed as a polynomial in the trace of that element. So by the 2 by 2 case again, just to give us a feeling what is happening, we can write the characteristic polynomial of any element inside the algebra of matrices by this expression. So this should give us inspiration that should be nice to generalize the trace of that we have for the matrix algebra for other algebras, other non-commutative algebras too. And this is a very technical slide, but the thing that we should take from it is that we actually can define a map that could be thought as the trace of the algebra. And, oh, sorry, again. And that this map is the same map that we happen to have in the algebra of matrix. And the other thing that using that map, we can define a formal and characteristic polynomial for the elements of that algebra. So the things that we can extract from this slide is that we can generalize the notion of trace, and we also can generalize the notion of characteristic polynomial for an element of my algebra. And I will call this n characteristic polynomial of my algebra by the Cayley-Hamilton identity for my elements. And if I take degree n, then this will be identity of order n. So an algebra that for every guy inside the algebra, it vanishes its nth order Cayley-Hamilton. I will call it an Cayley-Hamilton algebra. And it's not hard to see, it's trivial to see that the matrices are a Cayley-Hamilton algebra. And more generally, it's possible to prove that whenever R is a commutative ring, the ring of matrices with coefficients in that commutative ring is a Cayley-Hamilton algebra. So now, if we consider all the possible Cayley-Hamilton algebras or as a category, or all the possible trace algebras as a category, where the objects are the trace algebras and the morphisms are morphisms that preserve my traces, it's natural to ask what algebras can I put inside, or what algebras can I embed inside the ring or the algebra of matrices? And you should ask, why do you care about it? And well, we know how to work inside the algebra of matrices. So if we can work this more general algebra inside its image in the embedding, it will be better. So to deal with this problem, we need to introduce the notion of a universal pair. So here, again, we need some definition. I will try to explain what this definition means. So a variety for guys working with PI theory or PI algebras. It's not the variety that we are used to, but it's just an algebraic concept. That means that the algebras inside this set, that we call variety, are closed by taking homomorphic images, or that means if I have a homomorphism between two algebras, the image is again an algebra of the same type. Subalgebras inside these varieties, again a subalgebra of the same type, and arbitrary products of varieties of the same type is again a variety of it's again an algebra of the same type. So we'll fix a group G and work of the variety V of degraded non-associative algebras. So now we are considering very ugly algebras. But nice examples of this kind of stuff are when we consider G as Z2, and then we'll have superalgebras. Or we can consider, for the non-associativity, we can work with the octonions. So these guys appears in the nature. And again, and more, we say that an algebra is central simple if it's a simple algebra, and its center, it's isomorphic to the base field K. The first result that we have is that if we fix a variety of a type of properties that we want inside of an algebra, and consider two algebras, the first one, A, being finite dimensional and central simple, oh, sorry. Then we actually can find a commutative associative algebra S such that we can find homomorphisms B, a homomorphism Ho from B to A tensor with this commutative algebra, such that these two properties holds. So the first property says that the image of my B is finitely generated, and the second property is a universal property from this Ho and this S. So this is how you should read this result. So, with this in mind, it's not hard to see that the problem of embedding algebras translates to the problem to find a Ho and an S, such that this map Ho is a monomorphism, because in this way we can see Ho B inside A times S as the homomorphic image of this guy, and hence why we should have a variety. And this guy, Ho, and this commutative algebra S that we find in the previous theorem is what we call a universal G map. Again, G because we have a G grading. And it's possible to prove that this a universal G pair, or G map, is unique up to G graded homomorphism. And this is what I just said, that to have an embedding problem is the same as to have this Ho a monomorphism. So this notion of universal G map was proved in less generality for a lot of mathematicians. And in particular, Procesi had the result that if this B is a K-algebra with trace, satisfying the N Cayley-Hamilton that I showed you, then you can embed B inside the space of matrix, the algebra of matrix. And moreover, which is very nice, that we have that the image is isomorphic to the ring of invariants of our matrix by the action of GLN. So this is done in this work, and I will go a little faster here. So we can generalize this result by consider algebras that are not truly just non-associative, but we need a little constraint, so we consider power associative algebras. So each subalgebra is associative, but A is not associative. And we consider the sum of AK as the sum of the direct sum of A algebra. And we consider a subgroup of the endomorphism of my algebra acting diagonally on K, which I call calligraphic G. Again, I need a lot of results here, a lot of notation here. But I will try to translate. I will need my algebra to satisfy those properties. So I need the elements generated by the trace of my algebras to be to coincide with the ring of invariants of that group that I fixed before. I would like my trace, the trace that I consider, to be non-degenerated. So whenever I have the trace given 0, I would like that for all elements, I would like my U to be 0. I would like my group to be linearly reductive. And I would like to have a common upper bound for the length of monomials inside the trace. So all these conditions are technical conditions that we can prove that actually happens in algebra, in good algebras appearing in the nature. So under conditions P1 to P3, we can prove that indeed, if we start with a power associative algebra, that means an algebra that is non-associative, but each subalgebra is associative, equip it with a group G, with an action by a group G, and consider, again, a finite dimensional central simple, and consider another algebra R in the same, with the trace belonging to the same variety, then we can prove that indeed we can embed this algebra R inside A times S. And again, we can prove that the image inside A times S is the elements generated by the invariants of the action of my G. And okay, this guy is almost finishing, and where is the geometry of all of that? And that if I add the fourth property here, and the property that my algebra B is finitely generated, then I can prove that all the maps that go to B to A times S are parameterized by the variety Vs, the proper sense. So S is a commutative algebra. We can consider the affine algebra generated by S. And we can prove that there is a bijection between the points of this variety with the morphisms of A. So this is nice because it gives us a classification of these morphisms. Not only we know that we can embed the maps, but we can understand how the maps behave. And the nicest condition is that even for non-commutative algebras, we have things like a concept of formally smooth, and which sometimes is used to compute the dimension of this non-commutative algebra. And the previous results give us that A algebra B will be formally smooth if the associated, this V of S of that commutative algebra is smooth. So we can give a criteria, geometric criteria, to prove that some algebra is formally smooth, where formally smooth means that thing up there. We can lift some morphism with some more conditions. And this, for instance, we can use this to prove that, for instance, the algebra of diagonal matrices is not smooth because it's associated with the double point, with the coordinate ring of the double point, for instance. So this is what I would like to say. Thank you very much.